Hi guys, in today's lesson, I'll be teaching us half-life, nuclear fission and nuclear fusion. And I want you guys to stay to the end of this lesson. If this is your first time coming across my video, I want you to subscribe to my YouTube channel at Divine Online Chemistry Tutorial. So let's get started with the lesson. But before I commence with today's lesson, if you have not watched my previous video on radioactivity, I want you guys to watch that my previous video, because today's lesson is radioactivity part 2. Go and watch the part 1 of radioactivity so that you get the full details and full explanation on it. So let's commence with today's lesson. I'll be starting first with what? With half-life. Now, what is half-life? The half-life of a radioactive element is the time taken for half of the total number of atoms in a given sample of the element to decay. I come again. The half-life of a radioactive element is the time taken for half of the total number of atoms in a given sample of the element to decay. For example, I'll be making use of what? Of cobalt-60. Cobalt-60 is a radioactive isotope. So I'll be making use of what? Of cobalt-60. Cobalt-60. So I'll be making use of what? Of cobalt-60. And I said earlier on that what? Cobalt-60 is what? It's a radioactive isotope. So we'll make use of this cobalt-60. For instance, if 8 grams of cobalt-60, please take note for instance, if 8 grams of cobalt-60 is having a half-life of what? Of 5.26 years. Now for instance, if 8 grams of cobalt-60 is having a half-life of what? Of 5.26 years. It means that at the end of this 5.26 years, which happens to be the half-life, the half of this cobalt-60 will what? Will decay, remaining what? Remaining half. So that's what half-life is talking about. Half-life of a radioactive element is the time taken for half of the total number of atoms in a given sample of an element to what? To decay. And for instance, I'll make use of what? Of cobalt-60, which is a radioactive isotope. And I said that, for instance, if 8 grams of cobalt-60, which is having a half-life of 5.26 years. Now, at the end of this 5.26 years, which happens to be the half-life, 4 grams, which happens to be the half of this 8 grams, we have what? We have decay, remaining what? Only half. That's what cobalt-60 is talking about. Not the whole part, not the whole gram that will decay, but just half of it is what will decay. Decay at the end of what? At the end of this 5.26 years. The same thing occurs. So 4 grams now what? Remains. Now what? 4 grams. Now at the end of another 5.26 years again, half of this 4 grams will also decay. Now if half of this 4 grams decay, what will that be remaining? It will be remaining what? 2 grams. 5.26 years. Are you seeing it now? So in another 5.26 years again, half of this 4 grams would have decay, remaining what? Only half. Half-life is talking about half-life of radioactive elements is the time taken for half of the total number of atoms in a given sample of an element to decay. So that's what half-life is talking about. So at the end, you can see that at the end of 5.26 years, half of 8 grams decayed, remaining what? Only 4 grams, which happens to be the remaining half. So at the end of another 5.26 years again, half of this 4 grams was decayed. So that remaining what? Another 2 grams. Same thing occurs. So that's what half-life is talking about. So from here, we'll be moving straight to what? The formula for calculating half-life. There's a formula for what? For calculating half-life. So I'll be introducing the formula to us right now. Take note of this formula, and the formula is, take note of this formula where we have T half equal to 0.693 over lambda. So please take note of this formula. Now in this formula, this T half is known as what? The half-life. Half-life. So please take note of this, that this T half is known as what? The half-life. So half-life is being represented under radioactivity with this T half. So please take note of this. And this T half is known as what? The half-life. Then what about this lambda? This lambda is known as what? Decay constant. So please take note of this, that this lambda is known as what? Decay constant under radioactivity. Decay constant. So please take note of what? Take note of this. Now under radioactivity, this lambda means what? Decay constant. Why this here have means what? Half-life. So with this formula, you can calculate what? The half-life of a radioactive element. We can also calculate decay constant, where you have give you what? Half-life. So please take note of what? Take note of this. Now let's talk about the SI unit of half-life. Please take note that the SI unit of half-life is what? Is seconds. Seconds. So the SI unit of half-life is what? Seconds. You can also write it like this. So please take note that the SI unit of what? Of half-life is what? Is seconds. They can also give you a half-life in days. They can also give you half-life in weeks. They can also give you half-life in years. But take note that the SI unit, the actual SI unit for half-life is what? Is seconds. So to please take note of this. So half-life, we still have, because so the SI unit is what? Is seconds. Now what about the SI unit of what? Of decay constant. Now please take note that the SI unit of decay constant is what? Per seconds, which is S raised power minus what? Minus 1 for decay constant. So the SI unit for decay constant is what? Is per seconds. So you please take note of what? Take note of all these that I've brought out right now. So from here, we'll be moving straight to what? To nuclear fusion. Now, what is nuclear fission? Nuclear fission is the process whereby the nucleus of a heavy element is split into two or more nuclei with a release of energy and radiation. So you please take note that nuclear fission is the process whereby the nucleus of a heavy element is split into two or more nuclei with a release of energy and what? And radiation. Please take note that nuclear fission is different from what? From nuclear fusion. And I said earlier on that nuclear fission is the process whereby the nucleus of the heavy element is split into what? Two or more nuclei with a release of energy and what? And radiation. So I'll be explaining it on the board right now. Let's say, for example, uranium 235 92 emits a neutron particle, which is what? 1 0. Now if it emits a neutron particle, and I said earlier on that nuclear fission is the process whereby the nucleus of a heavy element, the nucleus of what? Of a heavy element split into what? Two or more nuclei with the release of energy and what? And radiation. Now for nuclear fission to take place, there must be a what? There must be neutron. So please take note of this, that what? For nuclear fission to take place, there must be what? There must be neutron. Now this heavy element now will split into what? Two or more nuclei with a release of energy and what? And radiation. Energy must still be what? Must still be involved. So you should please take note of this. Now if this heavy nucleus splits out, now the product of the form will be what? Barium 14156 plus krypton 9236 plus 3 mole of neutron 1 0. So this will be the product that will be formed. Now, like I said earlier on, I said that nuclear fission is the process whereby the nucleus of a heavy element is split into what? Into two or more nuclei with the release of energy and what? And radiation. Now the heavy nucleus that was given here, that we're making use of now, is what? Is this uranium 235. Now this uranium 235 undergoes what? Nuclear fission. Now when you undergo nuclear fission, and I told you that for nuclear fission to take place, there must be what? There must be neutron. So please take note of this. Now it undergoes what? Nuclear fission. Then it breaks down into what? Into what? Barium 14156. It also breaks down into what? Krypton 9236 and what? And 3 more of what? And 3 more of neutron. So please take note of this. Now this equation just explains what? Nuclear fission. So it's the process whereby the nucleus of a heavy element, which is this one, breaks down into what? Two or more nuclei with a release of energy and what? And radiation. So you should please take note of this. Now in nuclear equation, after bringing out this, you check if they are what? They are balanced. So I'm going to check if they are what? They are balanced. Now we have we are going to solve for what? For the mass number. Mass number is always the one up, where atomic number is always the one down. So I'm going to solve for the one up first. You can now check for what? For the one down. Now we have what? 235 here. Now 235 plus this one will make it what? 236. So at the reactant side, we have what? 236 for what? For the mass number. Now let's go to the product side. Now 141 plus 92. 141 plus 92, you get what? 233. 233. So you get what? 233 first. Then don't forget that we have 3 more of neutron here. Now this 3 will times this one up. Now 3 times this one, which is actually the mass number for this neutron. Now 3 times 1 will be what? 3. Now 3 plus what? 233 will be what? 236. Are you seeing it now? So at both sides, so 233 plus 3 equals what? 236. So you see now that the mass number at the reactant side is what? 236. The mass number at the product side is what? 236. So it's balanced. Now let's go to the atomic number. We have 92 here and we have 0. 92 plus 0 is same thing as saying 92. So now let's come to the to this other side. Now 56. Please take note of this. 56 plus 36 is what? 92. So please take note of that as this 56 plus 36 here is what? 92. Don't forget that what? We have 3 here and then we have 0 at this neutron. Now 3 times 0 is what? Is 0. Are you seeing it now? So this 92 that we got from this 56 plus 36 plus the 0 that we got here will still give us what? 92. So you can see that the atomic number here is 92. The atomic number here is still what? Is still 92. So you see that the case is what? Is balanced. So this is all about what? Nuclear fission. I come again. Nuclear fission is the process whereby the nucleus of a heavy element, which is this uranium-235, breaks down into 2 or more nuclei, which gave us what? One for baron 14156 and plepton 9236, and also 3 more of neutron with a what? The release of energy and what? And radiation. And earlier on I said that for nuclear fission to take place, now there must be neutron. Don't forget this. And there must also be what? A release of energy. So please take note of what? Of this. So from here, we'll be moving straight away to the last part of today's lesson, which is what? Nuclear fusion. Now, what is nuclear fusion? Nuclear fusion is the process whereby 2 or more nuclei fuse or combine together to form just one nucleus with a release of energy and radiation. Now, nuclear fusion is just like the opposite of nuclear fission that I've explained earlier on. You know, in nuclear fission, I said that nuclear fission is the process whereby the nucleus of a heavy element splits into 2 nuclei with a release of energy and radiation. So in nuclear fission, one nucleus splits into what? 2 or more nuclei. But in the case of nuclear fusion, now 2 or more nuclei, they fuse or combine together to form a heavy nucleus with a release of energy and what? And radiation. So that's what? That's about what? Nuclear fusion. So for example, we'll be making use of tritium, right? Tritium, which is what? Which is an isotope of hydrogen, tritium 31 plus deuterium. Please take note that deuterium is also on what? An isotope of what? Of hydrogen, or deuterium 2,1. So if they add together, you're going to get, it will give us alpha particle, which is this, which is actually a helium nucleus, 4, 2, plus neutron. Are you seeing it now? Plus neutron. So in nuclear fusion, 2 or more nuclei, they fuse or combine together to form what? A heavy nucleus with a release of energy and radiation. Now, if you look at this very well now, tritium is one of the isotopes of what? Of hydrogen, and tritium is what? Is radioactive. Now, what about deuterium? Deuterium is also what? An isotope of what? Of hydrogen. Now, when they combine together, they form a heavy nucleus, which is what? This helium nucleus, which is what? And you know that this helium nucleus is what? It's also alpha, referred as what? As alpha particle, which is heavy nucleus. Plus what? Plus neutron. Are you seeing it now? So plus neutron. Neutron must be what? Must be evolved. So plus neutron. So tritium and deuterium comes together to form what? The heavy nucleus, which happens to be what? The alpha particle, which is the helium nucleus, cell with what? With neutron. Now, after bringing out this, you also check if they are what? They are balanced. Now, for the mass number, 3 plus 2 is what? Is 5. Is 5. Then for this side, we have 4. 4 plus this one is what? Is 5. So the mass number is what? Is complete. Now what about the atomic number? 1 plus 1 is what? Is 2. It's 2 for the atomic number. Then this 2 plus 0. 2 plus 0 is the same as saying 2. So mass number is balanced at both sides, same as what the atomic number is so what balanced at what? At both sides. So this nuclear equation simply explains what? Nuclear fusion. When two or more nuclei fuse or combine together to form what? A heavy nucleus with release of energy and what? And radiation. Of course, there must be what? There must be neutron. So you should please take note of what? Take note of this. So with this, we have come to the end of today's lesson. Please, if you find this class very interesting, I want you to subscribe to my YouTube channel at Divine Online Chemistry Tutorial. Bye, and see you in my next post.